given by the following equations: P by I and on top of that the move fraction constraint. These are the set of equations that what I mean by the ideal VAE. So the liquid is not strictly the ideal solution, it is being referred to as ideal or referred to as Raoult's law. We saw that for both the bubble pressure and the new pressure, we get explicit expressions, right, which we have already written down. And then we saw that now when we go to the modified Raoult's law, this may be regarded as IgM. IS is approximate. And so this would be this would still be IgM, non-ideal solution. So but here the equations are P by I. Because we present the gamma, which is a function of in general both the move fraction and temperature. And so because of that here, even in spite of the addition factor, so the bubble pressure, we get an explicit expression. And correspondingly the move fractions of the vapor phase can also be determined in bubble pressure and the yi. We get explicit expressions. For the new pressure we saw that this is not possible unlike in the case of the ideal. Here for the new pressure we need to have an iterative procedure, and we outlined that iterative procedure to calculate the new pressure. And so we have to do that, right, to calculate the new pressure. Now we looked at how the bubble temperature for the ideal VAE. By choosing a particular PC sand and dividing or multiplying depending on the case, and then we get the ratio PI sand by PC sand or PC sand by PI sand, and based on that we get an expression for the temperature, which is how we determine the temperature. Now it's possible to show for the new temperature also similar procedure. You go back to the notes and see how we handle this. Right? So basically what happens, the bubble temperature X is specified, right? So y, you apply the move function constraint on y and then divide the equations through by PC sat. So as to get the ratios of PI sat to PC sat and evolve an iterative expression which will help you determine the successive temperatures and the move fraction for the vapor phase. A similar procedure can be applied for the new temperature. You discuss it explicitly, but you have to work it out. Now, when you go to the non-ideal solution cases, very similar procedures can be applied. Same procedure effectively can be applied, only we have to determine the gamma. For that, we have to be given an excessive free energy model. Right? So instead of taking the bubble temperature which we have already handled, we now see the new temperature and see how the same procedure applies for the non-ideal solution case. If you know how to handle the non-ideal solution, certainly you should be able to handle the ideal solution case also. So let's take the new temperature under the modified Raoult's law. So the new temperature means y is specified and also p is specified, and you have to determine the temperature, the new temperature, and the move fraction of the move fraction vector of the liquid phase or the composition of the liquid phase. So the procedure is very similar. First, let's write down the equations. Pyi is equal to Pi sat of T. Y is given, so I said that the trick is to apply the mole fraction constraint to the variable which is to be determined. There is no point in applying the mole fraction constraint, the variable is already given. So I can now rewrite this as xi equal to Pyi by Pi sat gamma I. So far I am not getting into the specifications. I am just working on the equations. You have to see the procedure is algebraically valid. Right? So this is perfectly fine. And now I equal to 1 to this is valid for all points. So now here I take I equal to 1 to C and I equal to 1 to C. What would I get? So I get 1 on the left hand side, right? And then P can be taken out. And I get I equal to 1 to C yi by Pi sat of T gamma I of x T. So from which we now get so now this is fine. This is fine. P is known, so I don't have to do anything with it. P is already given to me, right? So we have to be careful. So the key point here is to get the ratio PC to Pi or Pi to PC. So here Pi is in the denominator, so I can get the ratio multiplied by PC. Therefore, we will be divided by PC. So that's the key. So we want to divide or multiply by a particular PC sat. Depends on whether you are dealing with the bubble temperature or the dew temperature. So if you write the expression out, the key is again, because it's a bit tricky. If you try to remember the algorithm, you might get bogged down. So it's important to keep in mind the basic principles. Both the algorithms of bubble temperature and dew temperature is given by Smith and Van Ness. There may be other algorithms available. The key is to apply the mole fraction constraints to the mole fractions which are not specified. And then get the ratio in ways. So you have to determine the temperature. So we want to isolate a particular saturation temperature measure. So I can now multiply by PC sat P times sum over I equal to 1 to C y by or rather PC sat by Pi sat. But the ratio now is dependent on temperature. Now I haven't checked, but probably Smith and Van Ness have also given a clue which of the component you take, isolate out and give a special status to it. There might be some reason, maybe it's the lowest or the highest that we have to check. But if I multiply this, then I get yi by gamma I. So everything is rigorous until this point. So now what do we do? So here if you see P is given, YIs are given, neither this is given, nor neither the temperature is given, nor the mole fraction is given. So all the steps until now are exact rigorous analytical procedures. Now I look at the problem and see what is the, then you will understand the purpose of doing all this. Look at the purpose of doing all this. My objective is to determine T and X, neither of which I know. And so obviously we have to assume, that's the first step. Right? So we need to assume some estimate we need to have. Because the ideal case is also iterative. So there's probably no point in going through the ideal case and getting the initial, just for getting the initial guess. So we have to arrive at some initial guess. T naught, of course, you can take as a weighted by the mole fraction, the sum, weighted sum of all the given initially, yes. Right? So the key is now we need to make this like this, the same idea. And here, because I need to determine this, right? T naught, because if I put T1 here also I don't gain anything, because all caught up in the activity. So I assume an x naught and a T naught, which means the right hand side now is completely determined. And then I say that I am going to find the new temperature, the new value of PC sat effectively first. That would then give me the new value of T of 1. So this is the same idea we used when we discussed the bubble temperature control. I'm seeing how we can apply the same procedure. The fact that it's now getting the non-ideal solution doesn't affect the algorithm. Only thing it affects is you have to calculate the gamma. Once you assume an x and t, you can calculate the gamma. That's the additional factor that you have to calculate. So you get t of 1 from this. Right? So the algorithm as it is given in split and minus is you proceed, or you can now get a general. You don't want to just oscillate between two temperatures. You can just record all the temperatures and create an iterative process. You can run a counter J starting from 0 all the way down. Right? So we can now write this as Pi1C DC sat by PA sat determine Tj. There is a J step. So when you put J equal to 1, you get the first temperature. When you put J equal to 2, so when you put J equal to 0, you get the first temperature T1. When you get J equal to 1, that's the second step, you get the second value of temperature. So you go on accumulating temperatures, and phi I is specified. So this is the basic iterative formula, right? So this is the once you arrive at this algorithm is going to get calculated. So from this I need to calculate Uj plus 1. So I can invert the andon equals to andon, and we can, that is very easily inverted. We have the logarithm of PC sat A minus B by D plus C. You can easily invert it. Once you have the saturation pressure, how do you find the temperature? That also it gives. Only the saturation pressure at a particular temperature, the boiling temperature at a particular saturation pressure, both can be found by the andon equation. It is a standard practice to give it as in terms of pressure as a function of temperature. We usually rewrite it in terms of temperature as a function of saturation pressure. This is a basic rule, and so the iterative process he says would basically end if less than some epsilon. So you have to verify. Now the Modified constraints we are imposing, but it will that be sufficient to ensure that the difference in the mole fractions, successive mole fractions are also strong. So it depends. This is what I think he is given. You can also put the constraint as we saw earlier. You can also say that we can put one of the two. The other is not under our control. So you put a tolerance on the temperature. Then the mole fractions we expect will be sufficiently close to each other. Not sufficiently, we don't know. It depends on what is your tolerance, right? So on the other hand, we could check for this. Less than some delta for all, and then we hope if this is checked, the temperatures would also be automatically close to each other, right? So it looks like we can put a constraint or a tolerance on the accuracy of one of them, either the mole fractions, all of them together, all the temperature. The other one would be correspondingly not as close as we want, but if you want that, also then we can adjust the delta. If you find the temperatures are not becoming sufficiently close in the execution of the algorithm, we can simply reduce the delta so that both the temperature and mole fractions are within the accuracy that we decide. Right? Right? The algorithm will stop when either of these conditions are satisfied. Are there any questions? So you should just review. Now the bubble temperature and new temperature, for both, this is one idea that is there with the other algorithms available. Right? So this is one algorithm. The important thing is you get the ratios of the saturation pressures, which Smith and Daniels pointed to the relatively weak function of temperature, and that contributes to a faster numerical convergence. Otherwise, each time you calculate the saturation pressure and the temperature daily, we saw in one of the earlier alternative algorithms. Right? What we find often is that the temperature just keeps oscillating under most fractions. We don't reach convergence. So because the determining factor for the temperature here is the ratio of the saturation pressure, which seems to lead to a more efficient algorithm. So you have to keep that in mind. Now look at these two cases for the bubble pressure and the tube pressure. So the ideal case you get explicit expressions. Bubble pressure for the non-ideal solution, again you get explicit expressions. Now when you come to the bubble temperature and tube temperature, a very similar kind of approach applies for both the ideal as well as the non-ideal, for both the bubble temperature as well as the tube temperature. That is something you have to keep in mind. Yes. Yeah, that is once this is satisfied, the xi is going to be given by the equation I wrote. Right? Xi will be given by this. So xi is equal to, this is what we have, xi of 1. For instance, xi 1, let's try. I first wrote this. Yeah, the point is right, we have not completed. Xi of 1 will be p yi. Yeah, that's what I'm just rewriting that. Pi sat on this question, I think is how, what is it? Since I have now found the temperature, with xi naught, I start with x naught and t naught. First, I find t1. So I can use that to calculate x1, right? So clearly it makes sense to. But here, of course, this is the contradiction. This is why we have to continue the algorithm, which is why the equation cannot be regarded as satisfied. Because on the one hand, I have xi1, but to determine that, I need x naught on that, because I haven't determined x yet. So I am still here. I have taken x naught and t naught. So that problem is there here between t1 and t naught. Now the same problem exists between here. So when this condition is satisfied, the success, that is why we have to wait until the successive modifications are within the tolerance limit. This condition is satisfied, and we can assume that this equation is satisfied. That is, the set of equations are satisfied. And correspondingly, the modifications are also satisfied, because we are getting all of the equals in the modification constraint. But the key point is that while the right hand side has the initial guess, the left hand side has the one we are determining. So unless they are matching to within a reasonable accuracy, we cannot say the equation is exactly satisfied. So that is why either of these constraints would have to be imposed. That is the stopping criteria. Once I have this, then what this means, let us say for j equal to 10, we get this. So at that point, so I have 10. So I can simply approximately replace this by 11. And so for the same values of the move fraction, the entire equation is satisfied. That we have to take it as amounting to solving the equations. Any other questions? So to summarize, what I am summarizing is easy to remember that for both the bubble temperature and tube temperature, either it is the ideal or the non-ideal very similar algorithm. Apply the Mohs fraction constraints to the Mohs fractions which are not given and try to get an equation which has, to determine the temperature. So you have to bring in the ratios of the saturation pressure by choosing one component saturation pressure as somewhat special, which we are going to determine the temperature from. Objective is to determine the temperature. So once you have that, the Mohs fractions can be determined, and then you continue the procedure until the tolerance criterion is satisfied. Now, for the only isolated case that stands out here is the new pressure, and we saw that how it was. You cannot get explicit expression. We saw a slightly different algorithm. It didn't really involve these ratios. So that is something you have to keep in mind, how that one works. Because when you look at these algorithms, seems to be each one will require a different trick to do that. Right? So you have to keep that in mind. The other brute force approach is the one I outlined right at the beginning for the working temperature. It has a double loop. If you see, I think the basic idea behind these tricks is to reduce one of the loops. If you recall the earlier case, we had two loops. One to satisfy the Mohs fraction constraint, and another to satisfy the successive values of the temperature or the Mohs fractions are becoming closer to each other. So both have to be satisfied. Now in these cases, for the ideal as well as the non-ideal solution case, it appears that in certain cases we can avoid the double loop and simply have one loop. So we are imposing the Mohs fraction constraint in a somewhat clever way, right? And getting an iterative formula. So you have to really think about these algorithms and then see whether there's a pattern, how you best understand that. The algorithm is as there is in the book I have presented. Right? So to find out, how you go about coming up with maybe an alternate algorithm, you have to think and see what is the purpose of doing all. The overall purpose seems to me that in these two special cases of the ideal solution, non-ideal solution, retaining the ideal gas mixture case, in some cases we can avoid, even in all cases we can avoid a double loop. Now I will introduce a case. We take just one case and later on come back to the other algorithm. What if this is not possible? So no longer we have low pressures that we saw that ideal gas mixture means low pressure. Everything has been low pressure. You can have vapor in low pressure, both are at the same pressure, liquid and liquid. So similar substances and low pressures, you go for Raoult's law. Continuing to have low pressures, but dissimilar substances, then the liquid phase cannot be treated as approximately ideal solution. You have to take the non-ideality into account. You can get ethanol water as a gas. Methanol water, for instance, the methanol and water are chemically quite different, right? But still it seems to work there. Methanol water seems to be a classic case of an ideal solution. But in general, any system that exhibits ideal azeotrope, if you know, right, then certainly ideal solution has to be completely given up. Ideal solution cannot even remotely be used to treat such a case. So we come to this. Now the question is, what if low pressure is not also is at a higher pressure? And of course, if the pressures are high and the substances are similar, then we might treat the vapor phase. So that's the third case we can consider. Pressures are high but similar substances. Then we have to treat the non-ideality in the vapor phase, but still continue to treat the liquid as an ideal solution. So the right hand side of Raoult's law will remain as it is, being static and fixing. You can see the more complicated case because I want to find out the complications that arise, not so much from the norm, but rather from the non-ideality of the vapor mixture. So consider. If I can consider them together, because if I know how to treat this, then I certainly know how to treat non-ideal gas mixture and ideal solution. That's a special case. And we may have to make the more complicated case. So now, We will first take the bubble. So for bubble pressure, we got explicit expressions in both cases. Now we will see that that will no longer be possible. So we take that as a test example. Now this has to be multiplied. The fugacity coefficient is the one that gives the fugacity, the actual fugacity. And for the ideal gas mixture, the fugacity coefficient of each component is 1. So the fugacity of each component in the mixture is equal to its partial pressure. The easiest way to retain the form of the equation but modify it then to take it upon the non-ideality of the vapor phase is to introduce the fugacity coefficient. Very importantly, it will be a function of the temperature and pressure, of course, but also of the mole fraction. Temperature and pressure and the mole fraction. All in general, we have to assume it depends on the I equals 1 to C. And they still left with the mole fraction, that is 3. So now let's take the bubble pressure, the one that has not given us any problem at all, and we now see why it is going to give a problem. Because the bubble pressure is simply sum. What does bubble pressure mean? X and T is given, and you have to determine Y and T. Bubble pressure. Right? Given X, determine P. Obviously, then the pressure has to be given. So first of all, the trick that we employ for both the ideal solution and non-ideal solution is to sum this over I equal to 1 to C, and then we give an explicit expression for the bubble pressure. Because of the fact that the pressure is contained here, right? And also, of course, Y is, even if this were not a function of pressure, still Y, it is not known, is also there. It's all linked up in tandem, right? The temperature as well as the vapor mole fraction, the variables which you have to, the pressure and the vapor mole fraction, they are all in this. So I cannot, I can sum. I can put some I equal to 1 to 0, I am not going to get anything out of it. Okay? So in these cases, now you will see a certain similarity between the different cases. Bubble pressure, dew pressure, bubble temperature, they all would follow a certain similarity. So in that sense, the more complicated algorithm will be more difficult to implement numerically. In terms of algorithm structure, right, they would all start looking similar. So this kind of difference we had, for one of them being easier to determine or some special algorithm in one case and certain tricks in some case, certain other tricks in another case, that is not going to happen. So now here the idea seems to be that you first write an expression for the mole fraction that we have to determine, rather than summing over mole fraction and all that is not going to work. So sum over mole fraction effectively gives you a pressure or something, right? So that is not going to work, or dividing by Tc sat to get the temperature and so on. So we know why y is equal. So that's what I want to determine. So write the exact equation. yi is Ei sat of T, gamma I of x T xi, I equal to 1 to C, divided by B. So here what is it that I know? E I know, X I know, T I know, but pressure I we forgot the important quantity, phi I of E Y. So I know that, this is not an explicit expression for yi because y is there, and I also don't know the pressure, right? Which is appearing as a variable here as well as within the fugacity coefficient. So if I look at this, E and X are known, but pressure is not known and Y is not known. So here is how we apply now the trick, and the trick would be make this 1 and make this. The way we know, I don't know either the pressure or the vapor mole fraction, so I have to assume a value for for all of them, right? So first clearly assume here of course we have the bubble pressure, we have explicit expressions from the non-ideal solution, but ideal gas mixture, so I will use that. So assume we need a easy guess. So clearly from that, I can calculate the new values of the moving fractions. So the way the algorithm works, and Weinstein has also a very exhaustive collection of these algorithms for effective. This is now for terminology. This is what is referred to as the phi gamma approach. The phi gamma means that the vapor phase is treated through the fugacity coefficient and the liquid phase through the activity coefficient. So we need to calculate the vapor phase fugacity. We need an equation of state, and for the liquid phase we need an excess Gibbs field. So there is a certain mismatch and dissymmetry or asymmetry between the way we treat the vapor phase and the way we treat the liquid phase. One, we are using the equation of state. In principle, the equation of state can give the properties of the liquid phase as well. Finally, we summarize what are the advantages, disadvantages, and the range of values. You have to note that the same mixture in the equilibrium, vapor and liquid, but we are using this fugacity coefficient. They are using the activity coefficient. So there is an advantage and disadvantage to that. So now this is what we have. So how does the algorithm proceed? So the algorithm, the way it proceeds is that we are not going to check the mode, because there is no guarantee now the mode fraction constraints are going to be satisfied. Why not? Of course it will be satisfied. Why I have one is absolutely no guarantee that it will be satisfied. The way the whole thing works is that we first check whether the successive, the two values, successive means we have calculated one, assume that now the first step I have calculated, right? So yi1 minus yi1, we check, right? So even though the mode fraction might not be satisfied at all, this is what I check. So if not, yes means we don't stop there, right? We can't stop. But no, we first consider the no. This will be the inner loop. So no means, right? So I can simply recalculate the whole thing. So no, this is not satisfied. Then this is what I have to do. So I will retain P naught. That remains as it is. So now there will be two loops. One loop will adjust the mode fraction. The outer loop will adjust the pressure. And there we will impose the mode fraction constraint. So this is, we are still in the inner loop. Let us say it is not satisfied. And then I can put the value I have calculated. You can also write it as j plus 1. But for now, I will keep it simple. Right? So whatever I have calculated, y of 1, that I put in y naught and go back to this equation. And calculate, I will be effectively calculating yi of 2, but I am just oscillating here between yi naught and yi naught. So I will get the new value of yi naught with the yi1 with the y1 that I have calculated, which I am now just substituting into y naught. So I am just making the new y1, the y1 that I have calculated into y naught and using the same formula. Right? So then I keep on doing this until this is satisfied. So once this is satisfied, then I ask, is sum over k equal to 1 to c yj minus 1 less than some delta? Then only, between other algorithms available, but this is one that I have found that I just makes logical sense, right? So then I check for the mode fraction value. So all along we do the update the mode fraction without ever worrying about what the value of the sum of the mode fractions is. There is no way of escaping from this. Right? So we have to do that, which somewhat you can see why the tricks that were employed in the other cases will avoid this. What is the advantage of that? That avoids this one of the loops. Right? So now the question is what So again, if this is S, then we stop. The Modified constraints are satisfied, right? And this is also satisfied. So there are two equations. This equation, even though we are determining y1, unless the two mode fractions are close to each other, two sets, so j and j plus 1 are close to each other, you cannot say this equation is exactly satisfied. So left hand side you are using one set of values, right hand side you are using another set, right? So, but if this is, we have now already established this, that means this set of equations is satisfied. But now we have to look at the other one. Bubble equation means this is the mode fraction constraint that will operate. So if this is satisfied, then everything is satisfied. Mode fraction constraint is satisfied. These equations are satisfied because of this criterion being satisfied. And so we stop. But if not, then what we do is that means the mode fraction constraints are not satisfied, means effectively the pressure that I have chosen is not the correct pressure. So we need to update the pressure. So roughly, okay, how do we update? Again, it is conventional to make use of how much, whether this is greater than 1 or less than 1 to determine whether the new pressure will be greater than the chosen pressure or it's going to be less than. So we can clearly see here, if the yi's are, of course, it's not that easy to determine it here because there's also p here. We don't know how this is going to depend on p. But roughly, this might be the dominating term. So we see that y is actually inversely proportional to p naught. So if the yi1 is the sum, then here it doesn't matter whether it is yj1 or yj0, because both are almost close to each other. Right? So I can do this. So now if the sum of the volume of fractions is greater than 1, then clearly I have underestimated the pressure. So I need to increase the pressure. Right? So clearly then that suggests that P of 1 is equal to P of 0, right, times sum over J equal to 1 to C. Let's just check it. This is going to work, right? So what I want is if the mode fraction is greater than 1, that means I want to increase the pressure. Sum of the mode fractions added to greater than 1. That means I've chosen a lower pressure, I need to increase the pressure. We'll check if this algorithm is actually doing. So if it is greater than 1, then P of 1 will be greater than P naught. And so I now employ this P1. Now I will just use that as the new P naught. And then go back to this. And of course, we may as well also do the other one. So I now put the counter back to the original value. Because here I am just operating between P0 and P1 and Y0 and Y1. So I know, because I need some new set of values to substitute and go through this. So then again I have to do this with this chosen value of new value of pressure. I need to do the whole inner loop and then go back and check and then do this. So this is how you can imagine the complication, because at each point the crucial point in calculating is this. You have to go back to the formula for the viscosity coefficient of a component in a mixture of any equilibrium state. What it requires is the volume. For that I have to solve the fluidity equation of state and get the corresponding volume also. It is hidden here. That will be the most critical part of the calculation. Right? So you have to take that into account. And not only that, it's also creating this double loop, and there seems to be no way of avoiding it. Not only the actual calculation of viscosity coefficient is difficult, but it also makes the whole algorithm, the fact that we have to take the non-ideality into account, the whole algorithm more tedious and complicated. Are there any questions? Yes.
After finding the P1 new peer pressure, we continue with the old mode fraction or
No, old mode fraction, because the one that I have reached, that is the new set I have reached, right? So, we are continuing with that. Because we have checked that they are not adding up to 1, right? So, I am using that. So, whatever I have calculated here, right? That it doesn't matter whether it's old or new, because this criterion is satisfied. They are almost close to each other. So whatever I have, that's why I put that. The y of 1 is what I am going to use, but I am going to use that as y naught here. So whatever I have reached up to here, which obviously now I am finding is not satisfying the mode fraction, I am going to use the same thing, even though I know that it doesn't satisfy the mode fraction constraint. Because there is no other way of. I don't have any other y to deal with. All I have done is made sure that the successive values of yi are close to each other. I wait until that is done, because there are two criteria. Successive values of y close to each other is necessarily meaning the equation is satisfied. But that doesn't ensure that the mode fraction constraint is satisfied. This is very important. You may tend to forget. Okay? So the way this loop operates, this algorithm is to have an inner loop which will make sure first that this equation is satisfied without worrying about whether the mode fraction constraint is satisfied, and use the mode fraction constraint criteria to update the question. There may be other algorithms which do it differently, right? But this is the way. Does it answer the question? It doesn't matter, and what I am saying is that here y0 and y1, I have two sets. The one that I started with and one I have used to calculate this equation. Use this equation to calculate. They are almost close to each other, but I might as well settle with the. It doesn't matter, but that is the one that I am going to use here. Right? Knowing very well that hasn't satisfied the mode fraction, but I am going to operate with a new pressure. But so you have to finally ask, when everything is yes, this is yes means the successive values of the mode fractions are close to each other, that means that equation is satisfied. This is yes means the mode fraction constraint is also obviously satisfied. That's all I need. Everything is satisfied, that means the chosen value, the P0 that I have been operating. So I calculate this P0, let's say. With the P1 has become P0, and I do the whole thing with the P0. And let's say I reach this state. Then I find the mode fraction constraint is satisfied. That is the pressure which I have updated is the current pressure. Right? So this is the way it operates. Now, as far as the other new measure and so on, you can try to work it out. And what we will do, because you can see that this is not going to be possible for us to numerically implement in the class, the assignment and all, because of the nature of calculations involved in this. What you will see, the assignment sheet is much simpler problem when it comes to BAE, but there is also a question of calculating the vivacity independently of the wave without having to do it iteratively. That you should be aware of. How to, given an equation of state and given the composition of the mixture and how to use the mixing rules and so on, and how to calculate this. So there is a whole range of problems here which we will attempt to solve starting from Monday. The Thursday is a holiday tomorrow, right? So we start Monday onwards. We solve the practice. Look at the assignment problem in detail. There won't be any more new topics introduced. The final topic would be the 5-5, where we need to treat the liquid also using an equation of state. We see when that is required. That algorithm obviously will also be even more difficult, because the liquid also you have to use the equation of state to calculate. Right? So that again we need to know how the algorithm looks like. Maybe we choose some other new measure or something, but you should be aware of how to construct an algorithm. I know we have looked at several cases. Right? So we'll see how that works once we complete solving some of these problems.